Okay, college algebra class, we are going to start chapter 3 notes here, which is dealing with quadratic functions and models. So we're moving out of the linear stuff and into some quadratics. All right, so this is, I'll warn you, this is a little bit of a longer section. They've included a lot in here. So if at some point you need to just pause the video, take a break, and then come back to it. All right, so what we're going to look at here, we're going to learn some basic concepts about quadratic functions and their graphs, what the parabolas look like and their characteristics. Complete the square and apply the vertex formula. So for finding the vertex, putting it into vertex form, there's two ways. You can complete the square or apply the vertex formula. We'll take a look at both of those. Graphing them by hand, and then there are some application problems. Okay, so it says recall that a linear function is one that can be written in this form, ax plus b or mx plus b. So for a quadratic function, we know that we're going to have an x squared term in there. So quadratic, this is what tells us when we see that x squared. And it can be written into this form, ax squared plus bx plus c. That's our standard form of a quadratic function. Okay, we know that the graph's called a parabola, and the a value is what determines whether or not it opens upward or downward. We know that that point is called the vertex, the highest or lowest point on the parabola. And some other characteristics, we know that there's an axis of symmetry that runs through the vertex, vertical line that runs through the vertex. The leading coefficient a controls the width, so if the value of a gets larger, technically the absolute value of a, then it becomes skinnier, and if it gets closer to 0, then it becomes wider. And I think they just have a variety of examples here. If this, do they have a standard one? Yeah, right here. So the blue one is like your standard parabola. You can see that when you get numbers that get bigger, like this green one, 2x squared, it gets skinnier. When you get a coefficient a that's smaller or closer to 0, it's going to make it wider. It just rises less quickly. When you have a larger coefficient, it's going to rise more quickly. Axis symmetry, it's always this, this vertical line that runs through the vertex. Just different examples. We know that when there's negative leading coefficients, they're going to open downward. Okay, so here they're just analyzing some things. We know it opens downward because, so right here it says use the graph of the quadratic function, determine the sign of the leading coefficient. Well, it's opening downward, it's negative. Find its vertex, so we can just locate that here. It's left 2 and up 5, so negative 2, 5 would be the vertex. And then the axis symmetry is going to be always the vertical line x equals whatever this x coordinate is. So x equals negative 2. Okay. They'll also sometimes ask us to list where the parabola is increasing, where it's decreasing. And so the x coordinate, again, of the vertex is the important changing point there as we read it from left to right. Now, typically we've done these in interval notation. So it's, it's increasing this part of our parabola. It's increasing, right? And then it's decreasing on, as we move past that. So as we follow it this way, it's now decreasing. So thinking of those x coordinates as we move from left to right, it's increasing from negative infinity until I get to this x coordinate of negative 2. So I'm going to write that negative infinity to negative 2. And then we're decreasing when we hit this x coordinate of negative 2 until we continue to move to positive infinity. So negative 2 to positive infinity is where it is decreasing. Domain on all parabolas is always all real numbers. And then the range is based on the y coordinate of the vertex, right? So those are ranges, y values. So the largest y coordinate is 5, and then all the other y coordinates are less than that. So y is less than or equal to 5, or we could say negative infinity to 5. And we would include the 5 on that one because it's a point on the parabola. Okay, vertex form. Okay, so now this is probably the most convenient form to put a parabola in for graphing, because when we look at it in this form, we can see h and k, which represent the vertex, and the a value is right there, which is going to tell us, how wide or skinny that's going to be and if it opens up or down. Okay. All right, so we are going to talk about the process of completing the square. There's also another way to do this, which is with the vertex formula, and that's probably the one you would choose to do more often because it's I think it's probably a little easier and quicker. Completing the square, what we do is we take the b value, so that's that linear coefficient there, we divide it by 2 and square it, and that's what we have to use to make a perfect square trinomial. But when we add that on one side, we have to add it to the other side. Or if we're just keeping it in everything on one side of the equation, if we add it on the right side, then on the same side of the equation we subtract it to keep it balanced. So, for example here, it says write this in vertex form by completing the square. So remember, vertex form was just that. F of x equals a times x minus h squared plus k. So we want to create a perfect square trinomial so we can have a binomial squared right here. So to do that, okay, so here are the steps. We're going to take x squared plus 6x. I'm going to take this 3, or negative 3, and you always just kind of slide it over because that's going to end up being part of our k value that's out here. Okay, I'm going to complete the square with these two terms so that I can have a perfect square right there. All right, so this minus 3, I'm not moving it to a different side, so it's still minus 3. All right. Now, the process for completing the square is to take this linear coefficient, the 6, you divide it by 2 and you square it, and that's always what completes the square right here. So 6 divided by 2 squared is the number I add, and so that's what the formula says back here. So it's that k value, divide it by 2 and square that, and then you are going to use that to create your perfect square trinomial. Okay, so right here, 6 divided by 2 is 3, and 3 squared is 9. So a 9 is what completes the square. All right. Now, I can't just add something to an equation and say it's the same thing, right? If I added it here, and then I'd have to add it to the other side, but I really don't want anything over here with the f of x. I want to keep everything kind of on the right side. So if I added 9 here, that means I have to subtract 9 to keep it balanced if I'm on the same side of the equation. Remember, with an equation, the equal sign is kind of like the balancing point of a scale, right? And so if I were to add 9 pounds on the right side, to keep it balanced, I'd still have to subtract 9 pounds on that same side. And this process allows you to kind of rewrite this equation or this function so that it looks like the form that's up here. So what we created right here is now a perfect square trinomial. It's going to factor into x plus 3 squared. Because if you FOIL this out or factor it out, you'd have x times x to get x squared, and then you'd have 3 times 3 to get 9, and the outer and inner terms would add up to that 6x in the middle. So we created a perfect square trinomial. We would combine these two now together, and we'd have minus 12. Okay, so now it's in that vertex form, and I know I can look at this now and I can see that the vertex is going to be negative 3, negative 12. Okay, so that's one method for putting it into vertex form. The method you're probably going to use more often is this one. It's finding the x-coordinate of the vertex by taking the opposite of b over a, and that'll give you the x-coordinate of the vertex. And then this just means to plug that number back in to get the y-coordinate. You just plug it back into the function. So let's look at an example where we do that. And this is probably the easiest, especially if there's a coefficient here on the x squared term, because that makes completing the square a bit more difficult. You have to divide everything by 3 before you'd start. But since we're going to use the vertex formula, remember that goes x equals negative b over 2a. That's going to give me my x-coordinate to the vertex. So negative b is negative 12 over 2 times 3. So that's negative 12 divided by 6, which is negative 2. Okay, now I want to do f of negative 2 to get the y-coordinate, right? So it's 3 times negative 2 squared plus 12 times negative 2 plus 7. So that's going to be 4 times 3 is 12 minus 24 plus 7. 12 minus 24 is negative 12 plus 7 is negative 5. Okay, so I've got a vertex of, right here I've got negative 2 for my x-coordinate, I have 5 for the y-coordinate. So they're negative 5, negative 2, negative 5. That's going to be my vertex, okay? Now we need to put it into vertex form as well, so we want to take care of doing that. And so all that we have to do there is just plug it into, rewrite vertex form. So we need to go a times x minus h squared plus k. That's what we're trying to fill in. So f of x equals, now do we have an a value other than just a 1? And in this one we do, it's a 3. So that's what we have to fill in for the a. We can see that, that's not going to change. So we're going to put a 3 there, and then we're going to go x minus, and now my h is the x-coordinate, right? So x minus negative 2, so that has to go to a plus, squared, and then plus k at the end. Well, my k is a negative 5, so if I add a negative 5, that's just minus 5. So there's my vertex form, okay? So it's negative b over 2a. That gives you the x-coordinate. You plug that x-coordinate in here, you get the y-coordinate, h and k, and then just you can get your a from the equation. All right, I did change this equation just because the one that was given to us puts the vertex at a fractional position, and it's still doable, but it just makes it a little bit messier, and it's not really the point of what we're doing here is to make it real tedious. So I changed it to a similar one, but why don't you write this one down and let's work with this because then we don't have to deal with having our vertex at a fraction position. Okay, so to graph these ones, so I would say let's put it into vertex form, and we can do it just like we did on the previous one. So we're going to go x equals negative b over 2a. Okay, so my b is a negative 4, so I want to go the opposite of that, positive 4. 2a, 2 times negative 2, and so that puts my vertex at 4 divided by negative 4, negative 1. Now I'm going to do f of negative 1. I'll plug that back in, right? So I've got negative 2 times negative 1 squared minus, minus 4 times negative 1 plus 2. All right, so that's going to be negative 2 times 1 is negative 2. Negative 2 plus 4 plus 2. So that's going to give me 4. Touching the wrong buttons here. Okay, so that's going to be a positive 4. Okay, so my vertex is going to be negative 1, positive 4, right? So I fill that in into my vertex form, and the a value is still a negative 2, so I'm going to keep a negative 2 out there, and then I'm going to have x minus h, so that's going to be x minus negative 1 or plus 1 squared, and then plus the k value, which is 4, and now it's in vertex form. Okay, so that's helpful for finding, or for starting my graph, because I can see, well, I found my vertex to be negative 1, positive 4, and I can see that in here now. Negative 1, positive 4. Remember, it's always the opposite of this one. So negative 1, positive 4. Let's put that on the graph right here. Okay, and then I'm also going to draw, this is my axis of symmetry that always runs through the vertex like that. Okay, and then what I would do here, and I think this is the way your algebra teachers did this as well, you're going to have an x, y, or f of x, whatever you want to call it. I'll just say y. XY table, and we can put a few values in there, but if there's an a value here, then I think what most of your algebra teachers had you do was make a third column and call it whatever that a is, so it's negative 2 times y, and then we can, and I think what, like I said, I think what most of your algebra teachers did was they said, okay, well, if our vertex is here, this is kind of like our new origin in a way, and that way, when I think of, I'm using the parent graph idea, so I can think of this y value is just the parent graph of x squared, because any shifting that we do, this plus 1 and this plus 4, that's going to be taken care of if we kind of translate our whole graph left 1 and up 4. And so we, in a way, what we do is we think of this graph right here with the vertex being right through that vertex point. Okay, so that's like our new origin right there. All right, so we're going to pick just a few. I usually just do 1, 2, and 3. Sometimes they don't all fit. But then what we do then, if we square the 1 right here, that's 1. If we square the 2, that's 4. If we square the 3, that's 9. And then what we do is we say, okay, well, that a value is going to stretch that out and flip it over the, the axis. So we take each of these values now, we multiply them by negative 2. So I get negative 2, negative 8, negative 18. And when I graph, okay, now I'm like, okay, I just use this column to kind of help me out in this process, right? So from my new origin, right here where the blue dot, where the vertex is, I can go right 1, down 2. I can go right 2, down 8. I can go right 3, down 18. And that one might not fit though. So I can go right 1 and down 2, which is this point. I can go right 2 and down 8. 1, 2, 3. Which is going to be there. I don't think the 18 is going to fit, but now we can use this axis of symmetry and just copy these points over. And then we've got a sketch of our parabola. Okay? It'll look just like that. So hopefully you recall this process. I didn't go into a lot of detail, but I think you've done this before. Okay? Find that vertex, graph it on there, treat that as your origin, and then you can just pick like a few points, like 1, 2, and 3 is usually what I do. And then just remember to do the A value, the third column, to stretch it out or shrink it, whatever that happens to ask you to do, and that's what gives it that skinnier shape. Okay, so there's a few application problems we're going to go through here. This next one is a common problem, and I think there's one on the quiz and the test, so I would pay close attention to this. Okay, so this one here is I'm pretty sure this is one that you're going to see on a quiz or a test or both. So it says ranchers fencing a rectangular area for cattle using the straight portion of a river as one side of the rectangle. He has so much fence, he's got 2,400 feet of fence. We want to find the dimensions of the rectangle to give it the maximum area for the cattle. Common problem. Okay, so we've got our river as one side. We're going to fence in an area that's rectangular like this, so we only need to fence in 3 sides, right? And it's rectangular, and what we know is that our total amount of fencing that we have to use is 2,400 feet. So the way that you basically set these up every time is like this. You're going to say, okay, if I've got 3 sides to use, I know that the opposite sides are the same. I don't know what they are, but I know they're the same. So you pick a variable and you let them be the same variable, usually x, right? Now, with the total amount that you have, you're going to say, well, I've used up x here and I've used up x here from my total, and that's what's left for this side here. So from 2,400, I'm taking away 2 values of x that are going to be used here and here. So that's how I'm going to represent the other side of this rectangular enclosure. Now, area, that's our function that we're going to be working with, because that's what we want to maximize. All right? We want to maximize that area. So our area, and in terms of x, they probably call it a of x because it's an area function with the variable being x. Okay, to find area of a rectangle, we multiply width times length, right? Length times width. So it's x times 2,400 minus 2x. Okay, so that's going to end up being a quadratic equation, because when I distribute this x through, I'm going to end up with a 2x squared there. Okay, so if I have a parabola, and it's going to be a parabola that opens downward because we have a -2 as our a value in this case, right? And so what that's going to give me when I think about a graph that looks like that, it's going to be a parabola that has a maximum value because it opens downward. So what we want to look at is, this would be our area, and then this would be our x value, which represents our width. So we want to find that x value that gives me the maximum area. To do that, what are you looking for? Well, you're looking for the vertex, because we know on a parabola that opens downward, the vertex is the highest point. Okay, so the quickest way to do that, use your x equals -b over 2a formula, and that's going to give you the x coordinate to the vertex, which is really what we're interested in, because it just wants us to state the dimensions. Okay, so -b, now this is a little backwards. This is my b here because, right, this is my quadratic term, my linear term. So -b would be -2,400 over 2a, which would be 2 times -2. So I'd be taking -2,400 divided by -4, which would come out to 600. Okay, so that tells me that this dimension right here has to be 600 feet. And that's the same as what this one has to be. So those two are going to each be 600, right? Well, what does that leave for the other side? Well, 2,400 minus 1,200 is 1,200, right? So the dimensions of our maximum area enclosure is going to be 600 feet by 1,200 feet. And we should be able to enclose x. We have 2,400 feet of fence, and that's going to give us the maximum area. We can multiply that out and state what that area is. It doesn't really ask for it. It just asks for the dimensions. Okay, so that's how you're going to do a problem like that. All right, so label your 2 opposite sides that are equal as your variable. The third side is the total amount of material you have minus those 2 those two values. Okay. All right, one more application that we're going to do. It has to do with, basically it's a position and velocity kind of a problem, which I know that you did a bit of this in your algebra classes before. Some of the notations, the v sub 0 is an initial velocity, the h sub 0 is an initial height, and so those values could be, for velocities, could be positive or negative depending on if the initial velocity is upward or downward. Okay, so what we're going to look at in this one, and I left the work here just to save a little bit of time. So this is our position function. So this is the height of the, in this case, baseball after a period of time in seconds, which is in t. Okay, so a baseball's hit straight up in the air with an initial velocity of 80 feet per second, which translates to about 55 miles per hour. Leaves the bat at an initial height of 3 feet, so that's where the he's coming across with his swing is 3 feet above the ground. And so if I use those specifics, my v sub 0 goes in here, right there, right? So that's my linear coefficient, and my initial height is the 3, and that's going to go at the end. Okay, so write that formula. We've got it right here. S of t equals negative 16t squared plus 80t plus 3. Okay, so with that, we can determine how high the baseball is after 2 seconds, because this determines height after a certain amount of time. So we can plug that 2 in for each of these t's, and that's what I'm doing here in part B. So it's going to be negative 16 times 2 squared plus 80 times 2 plus 3. And simplifying that, we get a height of 99 feet. All right. Now, the next follow-up question is to find the maximum height of the baseball and then support your answer graphically. Okay, so the maximum height of the baseball, what we'd want to do there is find the vertex, because that's where the maximum height is going to occur, right? Wherever that vertex is. So we're going to use this formula, x equals negative b over 2a. So that's negative 80, because our b value is 80, divided by 2 times a, will be 2 times negative 16, and we get 2.5 for that. Now what that 2.5 represents is time. So it's going to take 2.5 seconds for that baseball to reach its maximum height. Now to actually find that height, that's the y-coordinate of our vertex of our parabola. Okay, so we have to plug 2.5 back in. So plugging, I'm calling it s of 2.5 because it goes back into our s of t function. So negative 16 times 2.5 squared plus 80 times 2.5 plus 3. Calculate all that out. It'll be a calculator problem. You're going to come out to 103 feet. So that's going to be your maximum height. So maximum heights are going to be achieved at the vertex, and you'll state the y-coordinate. If the question would say, how long does it take to reach its maximum height? Well, it takes 2.5 seconds. That's your x-coordinate. Okay? And I think that is everything for this lesson.